Alright, we've got 3 girls and 7 boys, and we're going to seat them randomly around a circular table. What's the probability that the 3 girls are seated next to each other? Because of course the girls want to sit next to each other. So, they're the minority. They want to sit by each other. Alright, so there's our circular table. We've got a total of 10 kids, so let's assume we have 10 chairs around this table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's our 10 chairs around the table. And let's first of all look at probability. Probability is just the number of desired outcomes. Desired outcomes over the total possible outcomes. So total outcomes. All right, and we can just calculate those two things separately and then just divide. So the total number of outcomes, that's not too bad because we've just got 10 kids, and if we don't have any restrictions on where the kids sit, we'll just start at one of the chairs and we'll assign one of the kids that chair. Okay, so let's say we start with this chair right here. We've got 10 kids to choose from. So if we calculate the total number of outcomes that are possible with no restrictions, we would have 10 choices for the first chair, 9 for the second, 8 for the third, 7, 6, 5, 4, 3, 2, 1. Okay, we just multiply that all together and we'll get the total number of outcomes. And we write that as 10 factorial. That's just a shorthand way of writing out 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, it's a lot easier that way. Okay, so that's our total. And we're assuming here too that there's, these are distinct chairs. They're different chairs. And as long as we're consistent between the numerator and denominator, as far as, we're not going to worry about symmetry of the table and whether, we have the kids, just because we rotate the table, is that the same seating arrangement? We're not going to worry about that. We'll assume they're all distinct chairs. Okay, so this might be a rocking chair, and this might be a stool, and this might be a dining room chair. Who knows? This might be a folding chair. We'll just assume they're all distinct chairs. And again, as long as we're consistent with the numerator and denominator as far as what we assume regarding the order of the chairs, we'll be okay. All right, so there's our total. Now, the desired outcomes. We want the 3 girls to be sitting together. All right, so let's just treat them like a block. Let's take a block of 3 girls. So, one possibility is that we could put the 3 girls here, okay, in these 3 chairs. Okay, and so we put the first girl in this chair, and then we put the other two to, I guess that would be her left. All right. And there's basically 10 ways that we could move that block around the table, okay? Because we're just moving the starting position and then putting the other 2 girls to her left, okay? So there are 10 ways. So this is the desired part. Desired outcomes. Okay, we'll compute how many ways we can seat the girls, or seat all these kids so that the girls are seated together. Alright, we have 10 ways to seat this block of girls. Alright, 10 ways to put the block of girls. Now within that block of girls, we have to recognize that these are different girls. Okay, so maybe it's Alexandra and Brianna and Catherine. Okay, now that is a different seating arrangement than, say, Catherine, Brianna, and Alexandra. Okay, or Brianna and Catherine and Alexandra. Okay, those are all different seating arrangements. And how many ways can we seat this group of 3 girls? Well, we're going to have 3 choices for the first, and then 2 for the second, and 1 for the third. So it's just 3 factorial. Okay, so that's the number of ways that we can arrange this block of 3 girls. Okay, They're still sitting all together. We just have different ways of arranging the girls. And then effectively we've got a block of boys too. They're going to occupy the remaining seven seats, and they're all different boys. And so we've got seven boys to choose for the first seat in the arrangement, and then 6, and then 5, and then 4, and 3, and 2, and 1. Okay, so the number of ways to arrange the boys is 7 factorial. All right, so if we multiply that all out, that should give us the number of ways that we can arrange these kids so that the 3 girls sit together. All right, so, but I'm not going to multiply that all out because I want to calculate the probability, and I've got a numerator and denominator, and if I don't multiply that all out, I can see the factors easily, and I can eliminate common factors. For example, I can see a 10 and a 10, and if 10 over 10 is just 1. So let's do that. We basically have 10 times 3 factorial times 7 factorial over 10 factorial. And I'm going to write that as 10 times 9 times 8 times 7 factorial. Okay, that's just the same as 10 factorial. Because you can see here 7 factorial over 7 factorial is just 1. 10 over 10 is just 1. Alright? And 3 factorial is 3 times 2 times 1, so I can replace that. And I can see I have a common factor between the 3 and the 9. And I can eliminate a 2. And I have nothing left on the top except 1, right? So I've just got 1 on the top, and the only thing I have left on the bottom is 12. Alright? So our answer is that the probability that the 3 girls would be seated together if we if we just arrange these kids randomly is 1/12. And you can see that it really helps not to do all this arithmetic for the numerator and denominator. Let's leave it in factored form, and then cancel common terms and reduce it down, and then we can get it in lowest terms really easily. So, alright, so there's your answer, 1/12.